Generalizing the differentiation. Yeah. So basically in this video we are going to do differentiations but in an abnormal way. Like generally if we differentiate we either have d by dx or d square x by dx square or d cube x by dx cube, or let's say dn x by dx to the power n of some function f of x where this n belongs to a whole number. N belongs to whole number. But what do we do for the cases where n does not belongs to whole number? Yeah. Even for these as well, we first find a general differentiation operator and then we just plug in those values. Though the domain of n is just whole number, we just strictly plug in the values and see what it gives us. So that's the idea. Basically, like this idea comes from the other aspects of mathematics as well. For example, uh, at the beginning, this binomial expansion for 1 plus x to the power n, this was just limited to n being whole number, wasn't it? But later, when Newton and other mathematicians suppose that it could be used for others as well, and then when checked, it did work. Yeah, this was first one applied for whole number and proved for whole number only when, yeah, or n being whole number. But when they try to explore if it would work for other numbers or not, it did work. Like for example, if we uh, have 1 minus x and n being minus 1, it the series actually gives the 1 plus x square, this series which you all know. So it does work for negative numbers as well. Not just this, for the other formulas like cos theta plus I sin theta to the power n. At the very beginning, the n was just supposed to be whole number, but later they knew that for any real number n, it does work. Yeah, and just like this, our the factorial function was just for natural numbers, or yeah, natural numbers of whole numbers. But later on, they extended it to integrals representation, and when they had integral representation, they could just plug in any real value and then get the integral value. Yeah, so this is how they extended the factorial function, and it's now helpful. In the similar way, like it is the passion of mathematicians to just extend the domain of n. Though it was meant to be a whole number, now we just extend the domain and we try to plug in these values and get the answers. So now after this discussion, let's get on to some maths. Yeah. Yeah. Okay. So now, basically, we will first deal with d dx of x to the power n. X to the power n, it's just n times x to the power n minus 1. And now d square x by dx square of x to the power n, it will be n times n minus 1 times x to the power n minus 2. So this is n factorial by n minus 2 factorial times x to the power n minus 2. Yeah, so that is just nc2 x to the power n minus 2. Okay, so now if we have d dx of d cube dx cube of x to the power n, so that will just be n factorial by n minus 3 factorial x to the power n minus 3. So now we can generalize this. Yeah, so let's say dt dx to the power t of x to the power n will be n factorial by n minus t factorial times x to the power n minus t. So this is the formula that generalizes those integer values in terms of formulas, and now we just try to plug in any value, like just for the sake of enjoyment or so, and that will somehow in the future will be helpful. Okay, it has been for all those years, so we can just predict that. Okay, now I want to find negative. First of all, let us try some other values as well. So if we try to have d4 by dx4 of x to the power, let's say 6, so that will be 6 factorial by 6 minus 4 factorial, that is 2 factorial, times x to the power 6 minus 4, that is 2. So this is the answer. And now we will try to find this one. It doesn't make sense, yeah, but let's check if it does or not. Okay, so we get d to the power minus 1 by dx to the power minus 1, and for x to the let us say just for x. So this gives us here we will have 1 factorial, and there we will have 1 minus this minus 1 factorial times x to the power 1 minus minus 1, yeah, minus 1. This gives us 1 by 2 factorial times x square. This is x square by 2, which is integral from 0 to x. X, these two are different, okay, x dx. See, the differentiation raised to power minus 1 is just the integral as expected, though the domain of the n was not for any integer, but see, it does make sense, and this is what is interesting about mathematics. Okay, so the d inverse operator is just integral from 0 to x, yeah. Okay, so that was cool. Now let's get to other one, d half by dx to the power of x. So this is 1 factorial, yeah, and 1 minus half factorial by x to the power 1 minus half. Okay, and now this will be 1. Now half factorial is just root pi by 2, and x to the power 1 by 2. So this will give us 2 times root under x by pi. So this was our d half by dx to the power half of x. This was in fact a cool result. 2 times root under x by pi. See, we have generalized the differential operator as well, and these values will in fact make sense like one day, yeah, when people will be like smart enough to utilize them. And the last one was d half by dx to the power half of 1. First let us do for a constant. So d half by dx to the power half of x to the power 0. So that will be 0 factorial by 0 minus half factorial by x to the power 0 minus half. So that will be 0 by negative half factorial is just root pi times 0 factorial is 1, and x to the power minus 1 by 2. So that is 1 by root under pi x. This is the answer. So let us just quickly write this down. We have this one as 1 by root under pi x, which was a wonderful result, and the other one was 2 times root x by pi. This is 2 times root 2 times root x by pi, yeah, and then the other one was and then this one was just integral from 0 to x, integral from 0 to x bar dx bar, where x bar is the other variable. So this was it. Hope you enjoyed the video and got some new insights on how mathematicians develop new tools and new ideas. So this was it. Hope you enjoyed the video. If yes, do like, share, subscribe. Thanks for watching. Look forward to seeing you in the next video.